X will always be, for me, a CAD0 cube complex. And the last sort of thing we talked about was that there are these hyperplanes. So if you're imagining a CAD0 cube complex, maybe piece of it will look something like this. Then there are these things called hyperplanes, which you can think of as taking a mid-cube of some cube, and then whenever you hit a boundary cube, you sort of go off in all possible directions. That's sort of the informal way to think about it. And then we said, well, you know, there are these equivalence classes of edges, and a hyperplane is transverse to this equivalence class of edges. So this was a hyperplane. And with these properties, let me just recall these properties. One was that hyperplanes are embedded. So if you think about in a non-positively curved cube complex, then it can come back and cross itself. But in a CAD0 guy, they sort of go off and they never come back around and intersect themselves. So they're nice embedded guys. Hyperplanes separate. So every one of these guys separates into two components. Okay, which we'll call half spaces. Then each hyperplane is itself a CAD0 cube complex of one lower dimension, and then we had this Helly property. So if H up to Hn are hyperplanes such that I intersect Hj is non-empty, then the intersection of all of them is non-empty. Okay, it's kind of a Helly property for hyperplanes. There's this this notion, if you think about this, there's this nice carrier, the collection of all cubes that carry the hyperplane. It's a nice combinatorially convex object, and this can be generalized. So I think it was Haglund who generalized it for all combinatorially convex objects, subspaces of a cube complex. If they pairwise intersect, then they all intersect. So this is some sort of somewhat more general. This is true in more generality. But let's just focus on these properties. So this thing will tell you that if you have enough hyperplanes and your cube complex is finite dimensional, then you'll be able to find disjoint ones. You'll be able to, if your dimension is n and I give you n plus 1 hyperplanes, there'll be 2 disjoint ones. And if I take even more hyperplanes, then I'll be able to find maybe 3 disjoint ones. So I'd like to just show you one thing that you can prove with this. So if G is finitely generated group, then and G acts on X, a finite dimensional cat 0 cube complex without a global fixed point. Just write the word fixed point. So that's the same as having, as you know, for cat 0 spaces, that's the same as having an unbounded, having an unbounded orbit, right? Because bounded orbits have fixed points. Then there exists G and G with an unbounded orbit. So it'll tell you that, you know, torsion groups can't act on a finite dimensional cat 0 cube complex without having a global fixed point. So just to give you some idea of how you would do this, so just sort of a sketch of a proof. So you pick a vertex, and you know, you suppose your group is generated by elements S1 up to Sn, has some relations, and so then you can take some vertex inside of your guy, and there's S1 of V, there's an Sn of V, translates a V just under these guys. And you look at all the hyperplanes that are crossed by these paths. So we're going to take one skeleton paths joining V and S and V. So these are one skeleton geodesics. So shortest paths. So if you think about it from these properties of the separation, if you take two vertices and you want to understand which hyperplanes they cross, well, they'll end up crossing only the hyperplanes that separate them, and they'll cross them exactly once. Okay, so if you have two vertices, there's V and W, then you look at the hyperplanes that they cross. Okay, so this is V and this is W. Then those are precisely the hyperplanes that separate V and W. Okay, so you have these hyperplanes separating. Oh, so maybe we should record that. So remark, or well, you have to think about it a little bit. So the hyperplanes crossed by one skeleton geodesic between V and W are the hyperplanes separate them. So, okay, so you have these hyperplanes, so maybe give them a name, I don't know, let H be the collection of hyperplanes separating V from SI of V. Okay, for some I. So okay, so I take the union of all of these hyperplanes over here. Okay. So now, I guess I should use this. We have all this blackboard space. So we have this orbit's unbounded. So we're going to take a point really, really far away. So we're going to take a point like here. Okay? And I don't know how far it's going to be. It'll depend, something depending on this choice that was made here. Okay? So this is some GV. Which I'll think about later about how far I want it to be. Okay, and this G is some word in generators, or inverses of the generator, so it's some word like this. So I want to, I can write that here. So every, maybe we'll give this alpha. So alpha is a one skeleton geodesic between V and GV. So every hyperplane crossed by alpha is in the orbit of H. Okay, orbit of this finite collection of things. And well, there's another path joining V and GV, which looks like the path you would have in the Cayley graph, right? So you would have, let's see, something like, here's SI1 of V, here's SI1, SI2 of V, and so on. So on. This is a path, right? And all of these guys, these little subpaths, are hyperplanes along here are crossed by, okay, all the hyperplanes along each one of these pieces are translates of one of the hyperplanes in H. Okay, and hyperplanes that cross this path beta, which is also joining V and G of V, all of these hyperplanes also have to cross alpha, because the hyperplanes that cross alpha separate V and G and G. Okay, so that's that claim. So so pick a path of the form V, SI1 of V, and so on. V, G of V, and this is formed by translates of, maybe we'll call these alpha i's, right? So this is alpha 1 up to alpha n, these different paths. Okay, and this will tell you that every hype crossed by beta is a translate of some hyperplane okay, but all the hyperplanes crossing alpha will live inside there. Okay, so okay, so that means that you can find one guy, since this is really, really long, choose this to be really, really large. compared to the size of H, you can find many that are in the same orbit. Okay, so choose the distance from V of GV to B sufficiently large so that there are many and hyperplanes in the same orbit crossed by alpha. Okay, so you'll find many of them. And how many? Okay, how many? How many enough so that there are 3 disjoint ones? Okay, so you 3 disjoint ones. Here's one, here's another, and here's another. Okay, those are 3 disjoint hyperplanes. And these hyperplanes, well, they'll come with an orientation. They come with, right, there's a side, okay, that there's one half space. Maybe each one of them, you put a little arrow pointing towards some half space. And this is an idea that if you've, in Sarah's book on trees, you'll see, if you have 3 edges along a path and you give them orientations, 2 are oriented in the same direction, that's all. Okay, so maybe these 2 will face each other, but this guy has to choose, right? So there'll be 2 that are oriented in the same direction. So this here will be maybe GH, G1H, and this will be G2H. So the element, whatever it is, G2, G1 inverse that carries this to this, will be a hyperbolic element, okay, because it's carrying a half space to be inside of itself. And this will produce a hyperbolic element inside of this thing, so an infinite order element. So that just goes to, it's a very simple kind of argument, not a whole lot going on over here, but there's all that's feeding into it is this really tele property in the separation. So if you have 2 half spaces that are nested, one inside the other, and you have a group element carrying this into that, this half space into itself, well, you know, the power, yeah, if this is, whatever this is, AH, then this H will have to be inside of AH. Okay, and so on. A to the n of H has to live inside of A to the n minus 1 of H. So this will be an infinite order element. Okay? So yeah, I mean, it's not necessarily hyperbolic in the sense of, this is a cat 0 space. It's not necessarily hyperbolic in the sense of contracting or anything like that. But it's an infinite order element. And it'll have an axis and so on. Yeah. Just to get a point really far away. It's an unbounded action. Okay, so no global fixed point means that the action's unbounded. So it's using very little, and it's very tree-like. That's what I'm trying to convince you. I'm trying to convince you this is just Sarah's book on trees on steroids or something. You know, you add you add some you know, IMSc theory or whatever to say that they're disjoint hyperplanes, right? But you're sort of taking that same argument and you're getting the same kind of theorem. Okay, so yeah, so that's a whole other story. That's things aren't known there. So let me just say just a few more things. So I guess I can erase. So this uses finite dimensionality. This uses very, very strongly, right? This fourth property that I just erased doesn't hold for infinite dimensional cube complexes. So, so Osajda, this is very recently. The free Burnside group. So that's the group where you take R generators and you add all the relations that x to the n is equal to 1, acts without a global fixed point on a cat zero cube complex. So it's an infinite dimensional guy, and we'll talk about how you might build actions on cat zero cube complexes in a bit. And then this is very recently, Colon and Girardel. So this is this year. So there exists finitely generated torsion groups that act properly. So that's even, right? That's stronger than no global fixed point. Really. So can I now write what CCC for cat zero cube complex? Huh? Yeah. So is that okay? Or is that some people that have issues? CCC. Oh, I see. It's emotionally difficult for some people. Okay, so let's maybe not. Yeah? Oh, yeah? Okay. I see. Okay, all right. Well, we don't want anybody to get upset. Cat zero cube complex. I'll write cat zero cube complex. It's okay. Okay, so, yeah. Yeah, they're all infinite. I mean, it has to be because, so. Torsion groups cannot act properly co-compactly on any cat zero space, right? That's, properly co-compactly, right? So yeah, that's a whole subject of trying to figure out torsion groups acting on cat zero cube complexes. What? Finite dimensional in this Helly property. In saying that I could find 3 disjoint hyperplanes, I needed to say that if I have enough hyperplanes, I'll be able to find disjoint ones. So in these infinite dimensional complexes, I can have big families. Just think of one infinite dimensional cube. There will be infinitely many hyperplanes that all pairwise intersect. And they all intersect. So that's where that comes in. Okay. So here's one more thing that has to do with this, just using these separation ideas. So this is, if you want to look up the answers to this, you can look up this paper. So this is L2 embedding. So you can embed a cat zero cube complex into Hilbert space. So the idea is this. So consider the following map. So you're going to take a map from, well, first you're going to do it from the zero skeleton X. and you're going to map it to, what are you going to map it to? You're going to map it to L2 of the hyperplanes. So actually, yeah, okay, let's write it this way. I won't, anyway, in a little bit I'll change notation. But so L2 of the hyperplane, this is the hyperplanes. So for every vertex, I'm going to have a map or an element of L2. So an L2 of H means that for every hyperplane, I have to tell you what the value is. So, so pick a base vertex V0, and then phi V of a hyperplane H will be 1 if the hyperplane separates V0 and V. Okay, so this means H separates V0 and V. Okay, and 0 otherwise. So this is just a sequence of ones and zeros. We'll have finitely many ones because there are only finitely many hyperplanes separating any 2 points. So this gives you a nice, and you then extend in a nice natural way, linear way, right, to the cubes, right? So you can imagine how you would do this for the edge and for the squares and the cubes. See, they're all sitting inside of L2 of H. So to the cubes. This gives a nice, so part of your exercise is that this is a proper map. That's not very hard. This context means the inverse image of a bounded set is bounded. Okay? Okay, so that's the map, and the neat thing about it is that there's also a G action on L2, which extends the action of G on the cube complex. So define G acting on L2 of H. So G phi of H. Well, the usual thing you do is you do G of phi inverse of H. That's something that people often do. But you do that only for the case where the hyperplane doesn't separate V0 and GV, and when GV0, when it does separate, you flip it. So 1 minus G, sorry, not G, phi of G inverse of H. So 1 minus phi of G inverse of H. Okay, so that's an action. So you need to show that this is an action. You have to check. No, it's not that obvious, but it's true. This is an action, and it's an isometric. And G of phi V, it phi of GV, the thing you need to check. So that will tell you that it extends the action of G on the original cat-zero cube complex. That's how we mapped. We mapped V to phi V. So it extends this, this action. So you get this nice proper embedding into L. If you had an action without a fixed point here, so an unbounded action over here on X, okay, you would get an action, an affine isometric action on a Hilbert space, and that means that it doesn't have property T. So, so recall that G has property T. This is one of the definitions. Property T, you're supposed to always put parentheses or something, right? G has property T if every action, affine isometric action as a fixed point. So in particular, if you got a group acting in a way on a action, on a Hilbert space. So this would tell you that whenever you manage to get an action without a global fixed point on a cat-zero cube complex, or then you would have that it doesn't have property T. Okay, there's also a notion of AT minability, which is a proper action. So if you had a proper action on a cat-zero cube complex, then you get this. So so that's a nice thing to sort of work through. You think about this action and it's extending this thing. Okay, so that's so much for sort of things you can do just by thinking about the hyperplanes and their basic properties. Okay, so so the next thing I want to talk about is cubulation. So getting groups to act on that's actually true. That's harder. That's actually true. So if you had an action, if you had a fixed point in this action in the Hilbert space, it would turn out to be actually in X. That's something they prove in the paper. That's I didn't give that as part of this, but that's actually true. So if you had a fixed point, it would actually be in X. So that's a way of proving that if you had an action on a cat-zero cube complex with a bounded orbit, it would have a fixed point, even if it's an infinite dimensional cat-zero cube complex. Because it might not be complete. That's sort of, anyway, that's a, I didn't want to go there, but yeah, that's a question you might want to worry about, right? You know this theorem that says that bounded orbits implies fixed. That requires completeness. If I have an infinite dimensional cat-zero cube complex, it may not be complete. So that's one of the things they were doing in this paper. I'm just giving this the part that deals with getting groups to not have property T. That's the exercise. Okay, so okay, so cubulation. So well, I almost gave I think I gave an actual proof. Huh? What was what part was missing? I didn't. I found three hyperplanes. I found three hyperplanes that are disjoint. What part isn't there in the proof before I erase this? Right. So this is this G2, G1 inverse. It's a good thing you asked just before. This element carries G1H to to G2H. Okay, and it carries the half space into it. And that's enough to tell you that it has infinite order. Okay? It's strictly contained. Right. That's right. Okay. Happy? Okay, so now I can erase the rest of this. Okay, so now let's return to the notation, and so I'm going to change notation a little bit just because it's what I'm used to doing. So X will be our cat0 cube complex, as usual, and H will be the half spaces. So I'll write little h like this when I mean half space, and I'll put a little hat on top of it when I mean a hyperplane. And then I'll write H star for the complementary half space. Okay, so the picture is H hat, maybe H. So when I write H, I mean a half space I've chosen a side, and then there's H star, which is the other. Okay, so it's like little hats. I want all of these to be consistent. So notice, so H is a post set under inclusion. Okay, so you have these walls, if you're familiar with the term, right? We'll talk about that a little bit. It's a nice space with walls, okay? And it's discrete, okay? Because between two guys that are one's contained in the other, there will be finitely many hyperplanes, right? So this is discrete post set, and it has a an order reversing solution, right? So A goes, or H goes to H star, right? So if H is contained in K, then this implies that K star is contained in H star. So that's a certain notion that, so Roller looked at this, just this combinatorial thing and called it a POC set. Okay, so it's a post set with complementation. So C is complementation. So the collection of half spaces is and anytime and this is sort of the example, right? A space with walls. So you just think of a set, a collection, and a collection of subsets. What do I call it? Sigma. Okay. Closed under complementation. And oftentimes we'll want this discreteness, so will be a discrete POC set. So this discreteness in this setting means that the set of all A in sigma such that X is an A and Y is not A. Okay, that's take 2 points is finite. This is finite for all X and Y S. Okay, so you can okay, so the thing you might want to think about is just take the plane, so E2, and some family of lines. Okay, this will be some collection of walls, and it'll be discrete as long as you're limiting on each other. Okay, that'll be a nice discrete space with walls, and there are many situations where you come up with discrete collection of walls. Okay, it's a very kind of general thing. So there's one more notion that I'll talk about, which is finite dimensionality. Okay, so what does finite dimensionality tell you in terms of this? Now when we're focusing on this poset structure, okay, it tells you that there can't be too many incomparable elements. There's a bound on the size of elements that are incomparable. So so we'll say, so a space with walls or a Pox set has finite width. That's, I think, the term that they use in combinatorics is if there exists a bound on the size of a set, a subset, separable elements. Okay, so that's what a Pox set is. Okay, a Pox set is a poset with this order reversing involution. You also don't want that H and H star are comparable, but that's okay. That's part of the formal definition of a set. And discreteness means exactly what you think it means between any two elements. They're only finitely met other elements, and finite gives you a bound on the size of incomparable elements. Okay, so I often get the question of why. Ultimately, you can work just with spaces with walls and build. We're going to build a cube complex in a space with walls. It somehow puts the hand on the combinatorial thing. So, for example, this and this, right? These are two spaces with walls in the plane. Okay, even if you did something like that, right? You might imagine that you had something like this. Just maybe this will be some weird thing that defines, separate the plane. You'll say maybe there's this side and that side, and well, they're this octet, right? In terms of what's contained in what, it's useful to say. So it's useful to put your finger on the combinatorial gadget. The Helly property doesn't, so that's where this finite width. So saying that the Pox set is width for the case of a collection of hyperplanes, the complex is the same as that the complex is finite dimensional. Oh, the Helly property for these, oh, the actual walls, no, that. No, in fact, that's, you can take 3 families of parallel lines in the plane, collection of walls, and we're going to talk about how you build a cube complex from that. So yes, that's okay, that's good. This is not, you don't see a cube complex here at the moment. If you took 3 lines in the plane, families of 3 parallelism classes of lines in the plane, but there is a cube complex you can build that's sitting somewhere. Okay, so let's describe. Finite width will imply finite width. Right. Yeah, I mean, I guess we don't know what it means. But I think the point that if we look at the Pox set from this, then what are we? So you look at, say, these 3 half spaces. Look at 3 guys. All right, so there are 3 half spaces you can think of. This, this, and this. Okay? And they will pairwise intersect, but they will not intersect. Right? All have a point of interest. That's what's bothering him. So the Helly property isn't satisfied for spaces with walls generally. For lines in the plane, maybe. For if you did this for R3, imagine planes in R3, then they won't be bounding a complex. Just take this cross R. So there's a, oh yeah, okay, well you can do that exercise while we do the whole. So let's describe the construction, and then we see where things go. Okay, so we want to build. So we want to build a cat-0 cube complex from a Pox set. So I'm going to always assume discrete. And for what I'm going to talk about, I'm going to talk about finite width. It makes the exercises a little bit easier. You can do it without it. If you're talking about a space with walls, you don't need the finite width, but it'll be instructive just to think about that. Okay? So you want to build a cat-0 cube complex. You want to find these missing cubes that aren't there when you look at those families of lines. Okay? So so the guiding thing is to think about a cat-0 cube complex. So think first about a cat-0 cube complex, and the post set sigma to be this collection of half spaces. So how would you describe a vertex inside of here? Well, you're sort of making a choice for all of the hyperplanes. I guess you should do the hyperplanes in different colors, right? Each hyperplane will point in the direction of V. You can put a little magnet at your vertex, and that will orient all of these hyperplanes. Okay? So an ultrafilter, a scary word, but it's not scary, on a Pox set is just a subset, of sigma. Okay, so such that, well, for every pair A complement, So for every pair A complement, A star, either A is an alpha or A star is an alpha, and not both. So you choose for each one. And then you want this other property that also you're familiar with if you've ever thought about ultrafilters from your previous life, is that if A is less than B and A is in alpha, then B is in alpha. Okay, so you could think about it as you sort of transversely orienting the pairs sigma, sigma star in some way. Okay, you're choosing one side or the other, and you have to do it in this consistent manner, that if you made a choice for A, then you have to choose it for B. If you think about what happens for a vertex, okay, this is an example, alpha V, if this is a vertex V, that's just the collection of all half spaces that contain V. So if V is in X0 and sigma this half space is, then alpha V this is just the set of all H such that V is it. Okay, that satisfies this condition. This is also true for a space with walls, right? If I just take a point inside my space, an element of S, and I take all of the subsets that contain it, that'll satisfy that condition, right? Because the point can't be in A or A complement, and it'll obviously have this condition. Okay, so so remark here is that in this case, alpha V satisfies a descending chain condition. Right, so every descending whatever it is, H1, see if I can get this right, contains H2 contains Hn, terminate. Right? Because you can't, there are finitely many, between any hyperplane and any vertex, there's finitely many hyperplanes, so you can't go on forever. Okay, so for a pocket and an ultrafilter on a pocket, you can talk about it satisfying this descending chain condition. Okay, so given this sigma as before, right? This pocket with, right? That's discrete and finite width. Okay, we'll consider the collection of ultrafilters satisfying this I can write DCC, descending chain condition, satisfying the descending chain condition. Okay, so this will be the vertex set of our CAD0 cube complex. Okay, these guys, it satisfies this descending chain condition. And then right, so that will be X0. We'll call it X0, right? It's the set of all alpha. Satisfying descending chain condition. Okay, so then join alpha and beta by an edge if and only if beta is obtained from alpha by flipping one of the choices. So it's just alpha minus some A, and then union A star. Okay? So here's an exercise. This thing, let's call it alpha. We'll define this to be alpha A. Okay? So where you take alpha and you flip A. So alpha A is an ultrafilter if and only if A is minimal. Okay, inside of alpha. So you can. That's not too hard. You think about if it were not minimal and you flipped. You think you have to be coherent. If you think about it, at least the picture I was in my mind is you think of a bunch of lines in the plane. Okay, like you do here, and you put transverse arrows on things. And you're not allowed to put arrows so they point in opposite directions on two things that don't intersect. That's the sort of picture you have for all this. And so if you had two things pointing like this, and I flip this guy, okay, then I have something that contains an ultrafilter that contains two guys pointed in opposite directions, and that's not allowed. Okay, so that's something. But if you have, we took all the guys that have the descending chain condition, okay, so you can always find some minimal elements. Okay, and so then the next exercise is that if sigma is of finite width, so this you don't need anything for, but I'm just use finite width for this. Then x1, which is now we've added edges, right? This gives me x1, is connected. Okay, so if you thought about, say, this example of the plane with and then maybe add some other family like this. Okay? Okay? And you can try to think of how you would get from one satisfying the descending chain condition to the other. Okay? You have to get. Okay, so it's not a finite width. This isn't true. Okay, you can think of a situation. Yeah, so thank you for that. That's the next. Yeah, that should have been the next exercise. You're between here and here. So if I had an iPad, I would just shift this down, right, and put the next exercise in. That if you did this flip, is that alpha A satisfies the descending chain condition. Thank you. So you get this nice connected containing all the that satisfy this. Okay, so you can try to think of what that would look like. This this situation. And then for the xn, well, let's start with x2. So glue in squares whenever a fourth cycle appears. So it turns out, if you think about this, that what happens is you'll have some alpha, and then you'll have an alpha A. You'll have here alpha B. These are the two guys. And you'll have a vertex here, alpha A, B, where you flip both of them, if and only if A and B were incomparable. Okay? So this is if and only if A and B are incomparable. Okay, in a space with walls, it's when the two walls intersect, and you see all four regions, right? And so just glue in a square there, and what I'm not going to prove this to you, but it's a lemma. You can try to prove it. Is that x2 is so when you fill in these fourth cycles, you get something that's simply connected. And then xn, fill in missing cubes. So that just means whenever you see the boundary of an n cube, you just glue in a cube. Okay? So whenever there is the boundary of a cube in xn minus 1, attach a cube to it. Okay. And that's it. So, so for the case of finite width, so if sigma, so the exercise, and that's thinking just about this kind of stuff. That's not, this is a little bit harder, but this is just combinatorial playing around, that if sigma is finite width, this process terminates. So it's, at some point you'll just get a nice n-dimensional cat-zero cube complex. If it didn't have finite width, you could just go on forever. And there are various issues that come up that I won't delve into. What were you going to ask? That's, okay, yeah, that's the next thing. And this is cat0. The fact that there are no more missing cubes tells you that link of the vertex, it doesn't have any missing. So whenever you have, I don't want to go into too much. The only way you can get the boundary of an n cube, just like here, is to have a situation where you had a vertex and a bunch of incomparable guys. And when you have that, you actually have possible ways of flipping them. So you see the boundary, you actually see a cube there whenever you see you see it already, yeah? Whenever you see the boundary of an n simplex, you actually have generalized to dimension n. This is B, okay? So you would have, instead of just two A's and B's, you would have A1 up to AN, and they're all incomparable. And so then you actually see the whole boundary of a cube there. And so when you glued the cube in, you killed everything, and all the vertices were already there. So you can still, this should still bother you, right? What would happen in this case? So you should try to think what would happen. What cube complex do you get? Do you answer, or do you want to think about it? You should be able to answer that question. Do you want to answer, do you want to go home and think about cube complex you get for this particular Pox set, space with walls? This is discrete, finite width, no, nothing. The simplest think about that you can't see right away, right? If I did two families of lines, you'd just say it's just the square tiling. You're not even going to answer that question whether you hear it or think about it. You'll think about it. Thank you for the. Okay. Yeah, that's. Let's see. Why is it non-empty when you start with an arbitrary Pox set? Could it be? I guess you could construct me some guys where this. I haven't thought about it. The examples that I come up with from spaces with walls, so I guess you could maybe construct me some bizarre Pox set where. I don't think so, actually. I think for any Pox set you could build one. I have to think about that. Why for an arbitrary Pox set you could do this? I've actually thought about this at some point, but right now I couldn't tell you the answer. How you sort of start off by, picking a half space or picking some element, taking everything that you have to take, and then somebody's calling, and then and then you take some other. You flip all the ones that you can on this side that don't intersect, and then you move on to the next one. You might have to use the axiom of choice if you do arbitrary things. Okay, so that's something to think about. Okay, so about this, think about what the guys are in this particular example. That's the first example with this. Okay. Another thing to think about is if you want to delve afterwards into the realm of what's the opposite of a finite width Pox set? What's the most not finite width Pox set you can think? It's where you think of a bunch of lines in the plane, none of which are parallel to one another. Right? So that's just, you have something in its complement, and then nothing is comparable. You take all, okay? It's like I don't know if you want to call that the trivial Pox set. And you try to think what you build there. Okay, you end up just building some really big cube. Okay, okay. So think about this three-dimensional example. So if you, a nice example from the sort of the hyperbolic world is think of a surface, right? So S is a surface of genus. Surface of genus G bigger than 2, and you take H to just be any cyclic subgroup. Okay, this is a subgroup of I want it. S. So you're really thinking now about a curve on a surface. Okay, so it can be some horrible, okay, curve on the surface, and then you lift it, so you get a geodesic. And upstairs, if you make it into a geodesic, when you lift it, you may end up with families of lines. You get a family of lines, equivariant under the group action, but they may cross. Okay? So you should convince yourself this Pox set, so here you're going to take the half spaces. So L is the collection of lines, okay, where you have this curve alpha, which are lifts of alpha. Okay, so you think about that. And then you have this nice pattern of lines, so you get a space with walls. Each one of these lines separates the plane into two half spaces. Okay, so you get a nice, sigma is the nice collection of half spaces. So that's a nice exercise in hyperbolic geometry, is that this has finite width. Try to convince yourselves of that. You can't have too many lifts that are all pairwise intersecting. And so then when you build a cube complex from this, again, you'll build some, well, it could be a very large dimensional cube complex. Nothing's stopping this thing from being some horrible curve on the surface, but it will be finite. And so you'll get a nice cat-0 cube complex that it's acting on, and in fact, it acts on it co-compactly. Okay, so that's something that I didn't mention here. So if you had group action on this Pox set that preserved, right? You have group action that preserved the nesting, preserved the structure, or an action on the space of this wall to preserve the walls, right? Then you get a group action on the cube complex, right? It will just take, because it's taking half spaces to half spaces, it'll take ultrafilters to ultrafilters, and descending chain ones to descending chain ones, and so on. Okay, so you'll get a nice group action on the cat-0 cube complex of a surface group. Okay, and you may think that it's not that interesting, because you know everything about surfaces. What do you need these cube complexes for? It's maybe true. There's some work by Jonah Gaster on this, where he's thought about taking, say, a filling curve on a surface and building the cat-0 cube complex you get associated to it. And he can learn various things about the curve. For instance, it's, what was it? I think it was the length, extremal length of this thing over. I'm not quite sure. But you can record various properties of this curve on the surface in the cube complex itself. So there is something even in the world of curves on surfaces which you can learn from this cube complex. Okay, so my time is up. I'll talk more a little bit about this next time, and then we'll go on from there.